Hello everyone, hope you're all doing fine. Welcome back to another lecture on electrostatics. In the previous lecture on electrostatics, we have learned about motion of a charged particle in a uniform electric field. In this video, we are going to discuss few examples on motion of a charged particle in uniform electric field. So yes, my name is Vijay Krishna and you're watching UpPhys channel. Let's get started. Okay, let's look at the first example. I'm going to read out the question first. A small sphere carrying a charge q is hanging in between two parallel plates by a string of length L. The time period of pendulum, the usual time period of pendulum is T0. When the parallel plates are charged, that means when the source is turned on, the time period changes to T. Okay? Find the ratio of T by T0. Find the ratio of T by T0. Let us recollect some of the key points of motion of a charged particle in a uniform electric field. How does this uniform electric field is usually can be created? Okay, so if I take two charged plates, I mean these are the two thin plates, sheets. Okay, if this is positively charged and this is negatively charged, and the charge on this plate is minus q, charge on this plate is plus q. This plus q plate and minus q charged plate will create certain amount of field, electric field in between the plates. This field is uniform. This field is uniform. Most of the cases we used to say uniform electric field. This is how uniform electric field is created. Okay, this is the simplest way to create uniform electric field. So we have the uniform electric field. I'm going to take this off. We have the uniform electric field, right? Okay, we have the uniform electric field. We have the plates here. This is positively charged, positively charged, and this plate is negatively charged, right? And there exists electric field between the two plates. Now I'm mentioning the electric field between the two plates is E. Is E. Electric field between the two plates is E. Let it be. Okay. Now, now it is mentioned that there is a string. There is a string which is suspended from the positive plate, and the length of string is L. Length of string is L. Okay. Length of string is L. Length of the string L. Let it be L. At the end of the string there is a sphere. There is a sphere of mass m and charge q. Mass m and charge q. Okay, mass m and charge q. At the initial stage, let us suppose, according to the instructions, initial stage, the plates are like this, and these plates have been connected to a battery which is not started. Okay, this plate has no charge, this plate has no charge. A string is hanged from the plate which is upper plate, and its mass is m. Okay, now charge is q. Let it be. It makes no influence on the time period. If I displace this sphere little to the left or right, if I leave it free, it makes oscillations. The time period of this oscillation is mentioned as T0. This T0 is equal to this T0 is equal to 2 pi root over L by G. Okay, because the only force which is acting here is mg. Okay, so T is not is equal to 2 pi root over L by G. What if another force is acting, whether it may be downwards or upward? In such a case, we represent the time period as 2 pi root over L by G effective. G effective. We will find the effective acceleration in the downward direction, and then we substitute it here. We will get the time period equation. Okay. Wherever which is required, we use G effective. G effective. Okay. Now, so this is the expression for the time period of the pendulum that we have taken when the source is not turned on, when the plates are not being charged. Now, let us suppose this plate is connected to a battery which is turned on, on which is on. If this the plate which is connected to positive terminal will acquires positive charge, and the plate that is connected to negative charge will acquires negative charge on it. Okay, then we have positive and negative plates separated by a certain distance, and there exists electric field from positive plate to negative plate. As we all know, electric field always points from positive charge and towards the negative charge. Okay, so positive to negative, which is uniform electric field. Now what I'm going to do is, it has mass m, charge q, and length of the string is L. Now again what I'm going to do is, I'm going to pull it aside and leave it free. It makes oscillations again. Now the time period of these oscillations are 2 pi root over L by G effective. L by G effective. Okay, right. Now we have to find this G effective. G effective is nothing but acceleration. G effective is nothing but acceleration, which is pointing downwards. Now, what is the force which is acting on the object? I'm taking the object here, sphere. What are the forces which are acting? Mg, weight of the object is acting downwards, and another force which is Eq. Eq. What is Eq? Electric force. What is Eq? Electric force. Electric force on this charge. Electric force on this charge. That is also acting in downward direction, because the electric field is downward direction. Electric field is downward direction. When I place a positive charge in the electric field, it experiences the force in the direction of electric field. In the direction of electric field. Let's say if I would have I have placed a negative charge in the electric field, then what happens? It will experience the electric force opposite to the electric field. Okay, as I have placed the positive charge, it is experiencing the force in the direction of the field, that is downward direction. So both the forces are acting in the same direction, which is F net is equal to mg plus eq, again downward direction. These two are acting in downward direction, and F net is nothing but ma, which is equal to mg plus eq, right? Now this ma, let's divide this equation with m. Now acceleration is equal to mg by m is g, and eq by m. eq by m. This acceleration we call it as G effective. G effective. Why are we calling it as G effective? Because this acceleration is acting in downward direction. So G effective is equal to G plus EQ by M. EQ by M. Now, if I replace this G effective into this equation, I will be getting the time period of the pendulum when the plates, when the source is turned on, when the plates are being charged. So T is equal to 2 pi root over L by G effective is G plus EQ by M. EQ by M. Now, we are not asked to find the time period of pendulum when the plates are not being turned up or plates are being turned up. We are asked to find the ratio T by T naught, I guess. T by T naught. We know T, which is 2 pi root over L by G plus EQ by M whole by, what is T naught? T naught is here 2 pi root over L by G. 2 pi root over L over G. We have 2 pi on the numerator and denominator. We have root L on the numerator and denominator. What do we left with? T by T naught is equal to, this root G will goes to the numerator, root over G, this G will stays here, and EQ by M. So this is the final result that we are asked to find. So T by T naught is equal to G by G plus EQ by M root over. This root can be represented as 1 by 2, power 1 by 2. So where do we have the answer? This is 3 by 2, right, which is wrong. And here we have 1 by 2, right, sorry, here we have 1 by 2, right. So this is the correct answer. G by G plus EQ by M power 1 by 2 is the correct answer. I hope this solution is understandable, clearly understandable, right? Okay, let's move on to another example. Right, now an oil drop of radius r and density rho is held stationary in a uniform vertically upwards electric field. Okay, so we have the electric field which is in upward direction. I'm drawing the electric field. This is the upward field. Okay, now this is the electric field direction is upward. Okay, that means the plate here is negatively charged, and upward, sorry, the plate here is positively charged, the plate here is negatively charged, because field always flows from positive charge to negative charge. So we are given with this situation, the electric field strength is E. Electric field strength is E, let it be. Now an oil drop of radius r density rho is held stationary. Held stationary in the sense the net force acting on this oil drop is 0. Held stationary in a uniform vertically upwards electric field E. Okay. Now let us assume the oil drop is somewhere here. Oil drop is somewhere here. Okay, this is the oil drop. This is the oil drop. Okay, whose mass we are not given with the mass. Okay, and whose density is rho. Density is rho. Whose radius is smaller. Radius is smaller. Okay, we are not given with the mass of the drop. We can find the mass of the rod by using the given quantities. Anyhow, now let's read out the rest of the question. If rho naught is the density of air, this space between the two plates is not empty. It is filled with air. It is filled with air. That means when an object is placed in the medium, fluid, especially fluid like air, the water, when an object is placed in the fluids, it experiences the buoyancy force. Buoyancy force. That means we can even consider the buoyancy force in this case. Okay, now as this object will have certain amount of mass, its weight is acting vertically downwards, one force which has been identified. The other force which has been identified is buoyancy force, and the other force that we are looking into it, there is electric field which is acting in upward direction. Okay, if there is electric field, if it has a certain amount of charge q, which may be either positive or negative, then there exists electric force also. I'm going to give the statement again. We have identified the weight of the object. Because the object oil drop has certain amount of mass, it will experience weight, and there exists fluid, air. So there is buoyancy force upwards. There is buoyancy force upwards. If this oil drop has certain amount of charge, positive or negative, then it will also experience the electric force because it is placed in the electric field. So there are three forces. There are three forces. Okay. As we have positive or negative charge, it will have two cases. Two cases. Okay. Right. Now I'm going to discuss the first case now. First case. Okay. Let's discuss the first case. Okay. Now in first case, I'm going to take charge is negative. Charge is negative q, that means excess electrons excess electrons are there in the drop. Excess electrons are there in the drop. Now the liquid drop, I mean oil drop is this one. Oil drop is this one, right? Now weight of the object is acting vertically downwards. Weight of the object is vertically downwards, and we have buoyancy force which is acting vertically upwards. Sorry, buoyancy force is upwards, and we have another force. Since this drop is negatively charged, the force on this charge is not in the direction of electric field, rather it is opposite to the direction of electric field. That means the force, electric force on the charge is downwards. Electric force on the charge is downward. F is equal to EQ. F is equal to EQ. I think I made all the points clear here, right? Right. Now, so sorry, since it is negatively charged, it moves, it experiences the force in the direction opposite to the electric field. As the electric field is pointing upwards, the force on the negative charge is downwards, which is represented here, right? Now, as the object is at rest, the drop is at, rest. Drop is at rest. As the the oil drop is at rest, the net force on it is 0, which is possible only when the forces are being balanced. That means F upward is equal to F downward, right? Now, upward force is buoyancy force, FB, is equal to downward force is mg plus eq, right? Buoyancy force formula is rho vg. Here rho is density of the fluid. Since the entire volume of the oil drop is immersed in this fluid air, so I'm taking the entire volume of the oil drop. G, rho Vg is equal to m, mass of the oil drop. Mass of the oil drop is not given. This mass can be expressed in terms of density into volume. Density of the oil drop is given as, density of the air is, rho naught is the density of the air. So rho naught is the density of the air. Density of the oil drop is rho V. So this is the mass of the oil drop into G plus EQ. Clear till now? Right. Now we need charge. So EQ is equal to, I'm taking this one this side, rho naught minus rho into V into G. Now Q is equal to, Q is equal to rho naught minus rho. What is V? V is the volume of the oil drop. Volume of the oil drop is a is spherical, is having spherical shape. So 4 by 3 pi. What is the radius of the oil drop, which is given as r, as you can see here, which is given as r. So 4 by 3rd pi r cube. 4 by 3rd pi r cube. 4 by 3rd pi r cube into G divided by this E is taken to the denominator, E. Okay, right? Now this is the charge of the oil drop, so that this charge must be negative, right? So that the oil drop will be at rest in between the two plates, in the air, right? Now the thing is, we are not asked to find the charge. We are asked to find the number of electrons. To find this number of electrons, what we do is we use the quantization of charge. Q is equal to N into E. Number of electrons. We have Q here. We have Q here. Q is equal to N. N. Now I want to find the N value, that is Q by E. Q by E. Q is rho naught minus rho 4/3 pi r cube G. That means it is 4 pi r cube rho naught minus rho into G by 3 is there. 4 pi r cube G rho naught minus rho. 3 is there. 3 E. This E is also there, right? So this is the number of electrons excess number of electrons in the oil drop. Why we are saying excess number of electrons? See, if an object is positively charged, means we are not adding the protons, rather we are removing the electrons. There is a deficiency of electrons if an object has positive charge. If an object has a negative charge, then there is excess amount of electrons in that object. right? So in as this oil drop is negatively charged, as we have assumed, that means it has excess number of electrons. So these many excess number of electrons are there in the oil drop for this oil drop to be stationary in between the two plates in the air. Okay, is my point clear to you? Right now. Now let's look at the equation. Excess electrons, how many excess amount of excess electrons. Now let's look at the options. 4 by 3rd pi r cube, G 3 E G. Okay, this is wrong. 3 not there. This is wrong. Deficiency, not the correct one. This is also wrong. Deficiency, wrong. So excess electrons. Excess electrons means this one is correct. This one is correct, right? But there is an issue. Here we should have rho naught, and here we should have rho. Okay, for the electron and for this oil drop to be negative. Clear? Right? Okay. Now let's look at the second case. For the second case, the correct answer must be deficiency of electrons, 4 pi r cube rho minus rho naught. We will get the same answer again, but there is a difference, rho minus rho naught. Let's see what happens. Okay. So this is the answer, first case. Now let's look at the second case. I'm going to take this off. Let's say for the second case, I'm taking the positive Q. I'm taking the positive Q, and we have not excess electrons, deficiency of electrons, deficiency of electrons, deficiency, deficiency of electrons. Okay. Now if the electrons are deficient in the oil drop, then the oil drop will have positive charge. That is clear. Now however, this is still at rest. Now as this oil drop is positively charged, it will experience the force in the direction of field, in the direction of field. So what happens? This electric field will cause the force, electric field will cause the force in the direction of field, in the direction of field. Let me take this out. In the direction of field. Okay, so we have this electric field EQ, electric force EQ in the direction of field, because the oil drop is positively charged. Now we have another force, that is buoyancy force. Buoyancy force is FB, like I have mentioned in the previous case. Now let's write down the equation. Still the situation be the same. As this is at rest, net force is 0. Net force can possibly be 0. Net force on the oil drop is 0. F upward is equal to F downward. Upward forces are buoyancy force and EQ. Buoyancy force and EQ. FB plus EQ. FB plus EQ. FB plus EQ is equal to downward force is mg. Clear? Now buoyancy force will stays as it is, and this EQ comes to this side. Here we have EQ, and here we have mg is nothing but mass can be written as density into volume. Density of the object is rho, volume of the object is v into g. As I want to find the charge, I will take this entire term to that side. So let's take this out. Okay, right. So rho minus rho naught into Vg to Vg. So I'm going to find the equation for the charge. Q is equal to rho minus rho naught. Volume of the object is 4 by 3 pi small r cube g by, if I take this electric field to that side, it will come in the denominator. Okay, as we are not asked to find the total charge, rather we are asked to find the number of electrons, deficiency or excess amount of electrons. We are going to find the deficiency, number of deficient electrons. Okay, right. Now q is equal to ne, it will stay as it is. Now n is equal to q by e. N is equal to q is how much? 4 pi r cube g, 4 pi r cube g, and this time rho minus rho naught, rho minus rho naught. So let's change this one, rho minus rho naught, rho minus rho naught, rho minus rho naught, rho minus rho naught, g by 3 e. The rest of the quantities will stays as it is. Okay, now deficiency, what is it? Deficiency of electrons. For the case of deficiency electrons, the equation is 4 pi r cube rho minus rho naught g by 3 e by 3 e. This will be our answer. So these are the two answers that we have. Okay, right? I hope the solution to this question is clearly understandable, right? Okay, let's move on to another example. Another example. Yes. So we have the question here. Let's read out the question. A uniform electric field E is created between the two parallel plates. As I've been keep telling that uniform electric field can easily be created by using the two parallel plates arrangement. Okay, simple arrangement of, if we take sheets, two thin sheets which are being connected to a battery. If the battery is turned on, the power is turned on, then each of the plate acquires one charge, one plate acquires positive charge, the other plate acquires negative charge. Then there will be electric field created between the two plates, which is uniform. This is how we create the uniform electric field. So the arrangement is given here to make the make the question simpler, right? Okay. and an electron enters the field symmetrically between the plates. The term symmetrically in the sense exactly halfway between the plates. Okay. If this total distance is L, then this distance will be L by 2, exactly halfway between the two plates, right? Okay, this is clear. And let's move on to the next point. Between the plates with a speed v0. Since the electron is projected horizontally, its vertical component of initial velocity will be 0. I'm repeating the statement again. We might have experienced this kind of concept in horizontal projection. Let's say an aeroplane is taking a package, it is moving along the horizontal line, with certain speed. Let's say the package has dropped. Then what happens? Along with the plane, the package will move and it gradually falls away. It will have the parabolic path, right? So the same concept goes here. If an object is projected horizontally, its vertical component of initial velocity will be 0. I hope my point is clear. So vertical component of initial velocity is 0. So what I'm writing is ux is equal to v naught. Initial velocity along the x-axis is v naught, and uy is equal to 0. And the other thing, the acceleration along the horizontal direction is 0, as there is no force along the horizontal direction. Okay, and acceleration along y direction is eq by m, because we have been deriving this equation multiple times. So ma is equal to eq, only force that is acting, which is in the vertical direction downwards. So a is equal to eq by m, as it is acting along the vertical direction, I'm taking the component as ay. Ay, let's erase this one. Ay is equal to eq by m downwards. Eq by m downwards. Okay, this arrow symbol is indicating the downward direction. Now acceleration that we have determined. Now the other part is if the acceleration is 0, if I use the kinematic equations, Vx final velocity is equal to ux plus axt. axt. Now, now let's find t. Let's find t. So, as the horizontal velocity is v naught, what is the time taken for this particle electron to cover the entire length L? Time t is equal to distance by velocity v naught. Distance by velocity v naught, right? Okay, v naught. Why we are using this v naught constant velocity? Because in the horizontal direction the velocity remains same because the acceleration is 0. You will evident that here when ux is v naught, when ux is v naught plus ax is 0, ax is 0. So we have Vx is equal to V naught. Vx is equal to V naught. That means along the horizontal direction, its velocity remains same because no force is along the horizontal direction. There is no acceleration as well. So the velocity remains constant. So Vx is equal to V2. Coming to the next case, Vy is equal to uy plus ay t. Ay t. Now acceleration along y direction we know, which is eq by m, and initial velocity along y direction is 0. Y direction is 0. So I am taking this quantity as 0. Now Vy is equal to this Vx. This Vx is here, and Vy is equal to Ay. Ay is how much? Eq by m into t. T is how much? L by V naught. L by V naught. Sometimes you may be given with the time, not the length. In that case, you can directly use the time quantity here. You will be able to get the final answer. But here we are given with L and V naught, so I'm using L and V naught. Okay, both of them. So eq by m, L by V naught. This is Vy. This is Vy. I'm writing L by V naught. Okay. Now what we are asked to find? Let's see. Find the angle of deviation. Find the angle of deviation. What is angle of deviation? How do we find it? Let's say theta. Now here we have Vx. Sorry. Here we have Vx. Okay. Here we have Vx, Vx, and we have Vy here in the vertical direction. In the vertical, not in the upward direction. It is in the downward direction. Sorry. Vy. And the other thing is the charge is taken as q. Charge is taken as q, but we are given with electron. Electron is negatively charged. I'm discussing the general case here. Okay, you can use the given question. You can inject that given data into this final equations. Okay, right. Now v1. So the resultant will be in this direction, v, deviation. In that case, I've taken positive, right? In that case, it is Vx, and this is Vy, and this is V, right? Right? Okay. Now, so if that is the case, then how do we find this? Angle of deviation, tan theta. Angle of deviation, tan theta, right? Alright. Angle of deviation, tan theta. Tan theta is equal to Vy by Vx. Vy by Vx. So let's substitute. Tan theta is equal to Vy is how much? Eq by m L by V naught by Vx is how much? V naught again. So theta is equal to tan inverse of E Q L by m v naught square. So this is the deviation for the general case. If the charge is positive, charge is positive, charge is positive, charge is positive, then this will go here. Even if charge is negative also, we will get the same result. But I'm going, if the charge is positive, right? If the charge is positive, if this is the positive plate and this is the negative plate, then the field will be in this direction. Field will be in this direction. So the charged particle will move like this. Okay. So the net velocity v, here we have vx, here we have vy. This will be our angle theta. This will be our angle theta. Now charge is negative. Charge is negative. Charge is negative. If the charge is negative, if the charge is negative, then I am taking the plates again. Positive, 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 negative, negative, negative. Okay. Okay. So plus q I am writing here. Minus q. What is it? Minus q is projected like this. This will move in this direction because this negative charge will be attracted, more attracted towards positive charge, so it will bend towards positive charge. It will bend towards positive charge, and here we have positive charge. Positive charge will move more attracted towards negative charge, so it will bend towards negative charge. Okay, right. So in this case, the velocity will be this one v, sorry, v, and we have x vx, we have vy, we have vy. This will be our angle theta, as you are asked here, theta. I'm going to take this entire thing off. Okay, as you right now we have this vx, this vy, and v. Why we have taken this upward vertical component of final velocity in upward direction? Because we are given with negative charge. What is it? Two parallel shown, an electron which is negatively charged, so the final equation will be I'm writing it here. Okay, theta is equal to tan inverse of e. In place of q I'm using e, charge of electron, e l by m v naught square. This is the actual answer for the question. I have used the general case. I have explained both the cases, right? If you are given with positive charge, in case of, in place of this an electron, you may be asked to find the angle of deviation for the proton. So you may be confused while where should we take the angle. Okay, so to avoid that confusion, I have explained both the cases here, and finally I've made use of the equation that I have derived, and I've applied it for the electron. So I hope the entire analysis explained over here is clear, right? And one more thing, I don't want to stop here. I want to extend the question little further. Okay, right? Listen to me. The actual path direction is this one, right? Actual path is this one, and the path is being deviated into this direction, right? By the time it clears the length of the parallel plates, you may be asked to find what is the vertical deviation or vertical displacement that you have acquired, that the electron has acquired. Let's find why. To do so, we have used the kinematic equations v is equal to u plus at till now, and now I'm going to use the kinematic equation s is equal to ut plus half at square. Let's make use of that kinematic equation. Till here the question is over, and now I have extended the question to find the vertical displacement of the electron by the time it exits the parallel plates or the electric field. Okay, right, let's do that. S is equal to ut plus half at square. As we are dealing with vertical direction, I am going to rewrite this equation as y final minus y initial. I am going to take this as displacement y, uy t plus half into ay t square, all the vertical components that I have used. Now vertical displacement y is equal to, what is uy? Uy is equal to 0, which is already there. So this will be 0, this will be 0, and half ay. Ay is how much? Ay is equal to eq by m. Eq by m, eq by m, and t is how much? L by v naught. That means we have L square by v naught square. L square by v naught square, right? L square by v naught. This is the general equation for the displacement, vertical displacement, for the vertical displacement, right? If you are asked to find the vertical displacement covered by an electron, then for an electron, for electron, y is equal to half e, instead of q we need to write e, we need to write charge of electron E, L square by m v naught square, m v naught square, for electron, for electron. If you are asked to find the vertical displacement for a proton, you will get, for proton also you will get the same equation, but the only difference is the direction of motion of the charged particle differs. For electron, it will be and this is positive, this is negative, positive, positive, right? This deflection will be in this direction for negative electron. Okay, for proton, for proton or positive charge, the deflection will be plus, 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 minus, minus, minus. Deflection will be this one. The deflection will be like this, right? This proton. Clear? Clear? In such a case, the deviation will be this one. Y goes down, y goes down. For an electron, y goes up. When the plates are, upper plate is positive charge, the lower plate is negative charge. Sometimes you may be asked a question in which the plates are being reversed. Plates are being reversed. Okay, I hope the entire explanation is clear to you, right? The solution to the given question is clearly understandable, right? Right. Let's move on to the next example. Next example. Okay, a particle, let's read out the question. A particle of mass 1 kg and charge 2.5 into 10 to the power minus 4 coulomb is released from rest in an electric field of 1.2 into 10 to the power 4 Newton per coulomb. See the quantities that are given. I'm writing here. Mass of the particle is 1 gram, which can be converted into kg, that is 10 to the minus 3 kg. And the other quantity which is given is charge of the particle 2.5 into 10 to the minus 4 coulombs, and we are given with one more quantity, that is electric field, uniform electric field, which is 1.2 times 10 to the plus 4 Newton per coulomb, Newton per coulomb. So these are the quantities that have been given to us. Now the first question that is asked is find the electric force and the force of gravity. Let's find electric force. Electric force, sorry, electric force Fe is equal to Eq. Fe is equal to Eq. Fe is equal to Eq. What is E? E is 1.2 times 10 to the power 4. And what is Q? 2.5 times 10 to the minus 4. What will be the answer? It is 1.2 times 2.5 is nothing but 3. 3 newtons is the answer. Now, we are also asked to find the force of gravity, Fg, which is equal to mg. Mass is 10 to the minus 3 and g is 10, which is equal to 10 to the minus 2 newtons. 10 to the minus 2 newtons, right? We have got both the forces. Now the question is still extended. Can one of these forces be neglected in comparison with the other? Yes, of course. One force is 3 newtons, the other force is 10 to the minus 2 newtons. That means force due to electric field is equal to 300 times force due to gravity. Force due to gravity. That means force due to gravity can be neglected in comparison with force due to electric field. Neglected. This can be neglected. This can be neglected. Okay, right. This can be neglected. So electric force is considered, gravitational force is neglected. First part answer is completed. Let's move on to the next part. How long will it take for the particle to travel a distance of 40 centimeters? Travel a distance of 40 centimeters. Okay. Now let's draw the electric field. I'm going to take the horizontal electric field here, as I've already ignored the gravity. Horizontal electric field that I've taken. Electric field strength is E. Electric field strength is E. And coming to electric field strength is E. And what is it? Second, how long will it take for the particle to travel a distance of 40? Let's say particle is started from here. Okay, charge Q is started from here and it is moved a distance of 40 centimeters. Moved a distance of 40 centimeters. That means we are also given with another quantity x is equal to 40 centimeters, which is 0.4 meters. 0.4 meters. And we are asked to find how long will it take for the particle to travel a distance of 40 centimeters. Okay, so let's find only one force is acting, right? So force net, F net, is equal to electric force, which is equal to EQ. EQ value is already determined, which is 3 newtons. 3 newtons. Okay, and let's find the acceleration. F net is equal to MA is equal to 3 newtons. I'm going to take off this Newton. Okay, 3 newtons. And acceleration A is equal to 3 by mass of charged particle. And we know the mass value. 3 by 10 to the minus 3, which is equal to 3000, which is equal to 3000 meter per second square. Meter per second square. This is the acceleration of the particle, which is uniform, as you can see. For a uniformly accelerated particles, we can make use of kinematic equations, right? So as you are asked to find the time taken and the displacement acceleration are known, we need to use S is equal to ut plus half a t square. S is nothing but the displacement. As we have the displacement here 0.4, I'm using that 0.4 here. Initial velocity of the charged particle. The charged particle is released from rest. So I'm going to take this off. Initial velocity is 0 and we have half here. And acceleration is nothing but 3000 as we have calculated, and this t we are asked to find, t square, right? What is t? T is equal to 0.8 by 3000 under root. T square here, root comes here, right? And if we solve it, we don't need to solve it. Even if we solve it, we will get 0.0163 or something, 162,163 or something seconds. Are we clear till now? Okay, right. Now, now we are left with one more. Part A is over. Part B is also over. Okay. Coming to part C. Part C. What is asked in part C? What will be the speed of the particle after traveling this distance? Okay. After traveling this distance, as we know time, we know the acceleration. We are asked to find the final velocity. So we can use the another kinematic equation. V is equal to u plus at. So this is the answer. This is the answer for part B. Part B. And this is the answer for part A. Part A. Now we are solving part C. Part C. Part C. We are solving parts. V is equal to u plus ut. We are asked to find v. We know u is equal to 0 initial velocity as it is released from rest. So initial velocity 0. We know the acceleration. Acceleration value is how much? 3000. 3000 into time taken is 0.0163. 0.0163 seconds. 163 seconds. So 1000 is multiplied. If we multiply the 1000, 3 into 16.3, 16 3s are 48, 48.9, what is it? Final velocity 48.9 meter per seconds. So this is the answer for part C. Part C. What is the speed of the particle after traveling this distance? I hope all the steps are clear till now, right? Let's move on to the last part. How much is the work done by the electric force on the particle? Work done by the force. Since the force is, constant, because electric field is uniform, so the force is constant. Work done by constant force. Part D. We are solving part D. We are solving part D. Okay? Part D. Sorry. We are solving part D. Okay, part work done is equal to force into displacement, right? In the direction of force only, the displacement has been taken place. So force is how much? Electric force is 3 newtons. All the quantities which have been already determined in the part A, and the displacement is already given in the question, which is 0.4, 0.4. What is the answer? It is 1.2 joules. Work done is equal to 1.2 joules is the answer for part D. Part D. Work done is equal to force into displacement. That force is electric force. Electric force is 3 newtons. 3 newtons into displacement is 0.4 meters. If I multiply 3 times 0.4, we will get 1.2 joules. 1.2 joules. Okay, I hope the solution to this question is very clearly understandable. And I want to discuss, few more questions. Okay, one more question. Let it be. Let's take one more question. Okay, which is very important. I think it has been asked in one of the mains questions, I guess. Okay, let's discuss one more question. Okay, now let's take two plates, parallel plates. One plate is, positively charged. The other plate is negative. Sorry, other plate is negatively charged. Okay till now. Now a particle of charge q of charge q sorry a particle of charge q is projected at an angle 45 degrees, at an angle 45 degrees to the horizontal, to the horizontal to the horizontal. Okay, now to the horizontal, a particle of charge q and mass also m is projected at an angle 45 in between the two plates, with kinetic energy k0. K0 is the kinetic energy, initial kinetic energy of the particle. Okay, now what we are asked to find is, what is the horizontal distance, or what is the length of the plate, what is the length of the plate required by the time, what is the length of the plate covered by the time it hits the plate again. Okay, as it goes like this, okay, it hits the plate again, right? It hits the plate again. We are asked to find this distance, which is nothing but range, that we already know. We already know, but the condition is we are given with the vertical, I mean the separation between the two plates as D, two plates as D. So we need to express this range in terms of D. Am I clear? Right? Right. Okay. Now, now, okay. So for this particle, maximum possible height is D only, right? Right? Do you agree with me? Do you agree with me? So maximum possible height should be not more than D. That means maximum possible height should be D. So I'm taking H max first. H max is equal to, it must be D maximum. So D is equal to U square sine square theta by 2g. Theta by 2g. And what is U square? U we don't know. Leave it as it is. U square sine square theta, sine square 45 degrees by 2g, by 2g. And here we have another problem, that is g is ignored. G is equal to 0. Let's say gravity free space, gravity is ignorable, but here we have electric field, right? Instead of G, I'm taking G effective here. I'm taking G effective here. So what can we replace G effective? EQ by M. EQ by M. What is E? E is the electric field between the two plates. Electric field between the two plates, positive to negative. Positive to negative. Electric field between the two plates, right? So EQ by M is the acceleration. G is 0. G is 0, and this acceleration due to electric field is acting in downward direction. Acting in downward direction. As you can see, as I have projected positive charge, the force on the positive charge is along the electric field. The electric field is downward, so force also in the downward direction. As the force is in the downward direction, the acceleration also in the downward direction. So the acceleration is downward. EQ by M. So if I rearrange this, sine square 45 is 1 by 2, 1 by 2, and we have this m upwards, and we have 2 here, 1 by 2 mu square, 1 by 2 mu square, and what do we left with? We have EQ in the denominator, divided by EQ, divided by EQ, and half mu square is nothing but initial kinetic energy, right? So if I rewrite this equation, H max or D is equal to half, what is it? Half E naught, I mean K naught, sorry. K, K naught half mu square by EQ, by EQ, right? So this is the distance D is expressed in terms of given quantities. Okay, now let us find range. R is equal to U square sine 2 theta by G effective here. G, instead of writing G, I'm writing G effective, because gravity free space, only acceleration that is acting in vertically downward direction is acceleration due to this electric force. So G effective, we know the G effective value, which is EQ by M. So U square sine 2 theta, sine 2 into 45, which is 90 degrees, by G effective is EQ by M. EQ by M. And what do we do? So mu square by EQ, this sine 90 is equal to 1, and we have mu square. If I multiply with 2, divide with 2, then this mu square by 2 can be written as kinetic energy, initial kinetic energy. So what am I doing is 2 times, okay, 2 times K naught by EQ, K naught by EQ, K naught by EQ. Now from this equation, I can write K naught by EQ is equal to 2 times D, right? 2 times D. Now, this K naught by EQ, it is here. This K naught by EQ can be replaced with 2D, yes or no? right? So if I replace k naught by eq with 2d, then 2 into 2d, 2 into 2d, 2 into 2d. Now what is the answer? The answer comes out to be range is equal to 4d. Range is equal to 4d. Okay, I remember this question actually, which which we use uh, motion of a charged particle in uniform electric field to solve it. Okay, which I think this question has asked in any of the mains exams, as I can remember. So the final answer is R is equal to 4 times D. 4 times D. I hope this question is clear, right? So at what distance from A or from the starting point the particle again hits the plate, which is nothing but range of the projectile, as I can say. Now let's move on to another simple final one more key point that I'm going to discuss now. While we are dealing with the time periods, let's say we have this pendulum, and the field is in downward direction. Let it be electric field. Okay, that means mg is acting downward and eq is also acting downwards, right? Now g effective will be is equal to g plus eq by m. Now the time period of the pendulum is equal to 2 pi root over l. L is nothing but the length of the pendulum. L by g effective is g plus eq by m. Instead of field in the same direction, downward direction, let's just say the field is in upward direction. Okay, field is in upward direction. Pendulum field is in upward direction. Electric field is in upward direction. As the field is in upward direction, weight is acting vertically downwards, mg, and electric force eq is acting vertically upwards. Now g effective will be how much? G effective is equal to g minus eq by m. G minus eq by m. Then how does the time period changes? Time period t is equal to 2 pi root over L by G effective is how much? Here we have G effective G minus EQ by M. EQ by M minus EQ by M. Okay, weight and electric force, if both forces are acting in the same direction, downward direction, then the effective G value is this one. If weight is acting downward direction and the electric force is acting in upward direction, then the effective acceleration due to gravity is g minus eq by m. Wherever it is necessary, whenever it comes to a concept of time period of pendulums, we can make use of these equations. And I also want to discuss one more key point here. I'm going to take this diagram. Okay, let's clear this page. Let's go to one more page. Okay, let's discuss one more key point. Vertical circular motion related concept. Let's say a particle is rotating in a vertical circle, but before that I've taken two plates. One is positive and the other one is negative, let it be, and there is a fixed point. From fixed point there is a string which is being held freely. Now, as we all know, if a particle to travel the entire vertical circle, minimum velocity required at the bottom is root 5gl. We call this velocity as critical velocity at the bottom, and as it moves in the vertical circular motion, the velocity required at the top is root gl, right? Root gl. Instead of using the g here, I can use g effective, right? Weight is acting vertically downward direction, mg, and there is electric field which is also pointed in the downward direction, like this. In that case, electric force also acting in the downward direction. This charge is q, mass is m. Both the forces are acting in the same direction, So the G effective will be G plus EQ by M. G plus EQ by M. And there is a possibility for the electric field to be in upward direction. In such a case, it will be G minus EQ by M. G minus EQ by M. Then the minimum velocity V at bottom. V at bottom is equal to root 5 G effective into L. L is what? L is the length of the string. L is the length of the string. So if I use this equation, G effective is equal to G plus EQ by M into L into V bottom, right? If it is a gravity free space, if G is equal to 0, then the equation will be 5, root over here, root 5 EQ by M L, EQ by M L for a gravity free space. Hope my point is clear. Let's say this electric field is in upward direction. This plate is positive, this plate is negative. In such a case, the equation would be G effective equation would be G minus EQ by M. G minus EQ by M. And at the bottom it is 5 G minus EQ by M. For gravity free space, it is again EQ by M. Clear? Till now every example, every solution is clear, and we have also discussed two key points at the end of the lecture. Those two key points are very important to save the time while solving the problems. Okay, so V bottom, if you want to write the equation for V top also, we will get V top is equal to root G effective. G effective is G plus EQ by M into L under root, right? So these are the examples that can be solved by making use of motion of a charged particle in uniform electric field. So yes, I hope the video is helpful. If you find the video is helpful, please like, share and subscribe. Don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. So that's it in this video. Thank you for watching. See you in